Chemical equations are shorthand notations that represent chemical reactions. They show the reactants, which are substances that start a reaction, and products, the substances formed by the reaction. For example, in the equation 2 hydrogen plus oxygen yields water, 2 hydrogen and oxygen are the reactants, and water is the product. Balancing chemical equations is crucial because it ensures the conservation of mass and charge. This means that the number of atoms for each element and the total charge are the same on both sides of the equation. Without balance, the equation would not accurately represent the reaction. In real-world chemistry, balanced equations are vital. They help predict the amounts of substances consumed and produced in reactions. This is essential in industries like pharmaceuticals, where precise chemical quantities are crucial. Failing to balance chemical equations can lead to incorrect conclusions. For example, an unbalanced equation might suggest that matter is created or destroyed, which contradicts the law of conservation of mass. Balancing equations ensures that we respect fundamental scientific laws. It also helps in understanding how substances interact during chemical reactions. This foundation is critical for studying more complex chemical processes. Hello, science fans! Today we will be discussing stoichiometry. Balancing chemical equations involves several systematic steps. First, write down the unbalanced equation. For example, hydrogen plus oxygen yields water. Second, count the number of atoms for each element. Third, balance the atoms one element at a time. Balance oxygen by changing the coefficient of water to 2. Adjust the coefficients to balance hydrogen. Finally, double-check the balance of all atoms and charges. Our equation is now balanced. Let's consider another example to solidify our understanding. We'll balance the combustion of methane plus oxygen yields carbon dioxide and water. First, write the unbalanced equation. We have methane reacting with oxygen to produce carbon dioxide and water. Second, count the atoms of each element on both sides. On the reactant side, we have 1 carbon, 4 hydrogens, and 2 oxygens. On the product side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Third, balance the carbon atoms first. Since there's 1 carbon atom on both sides, carbon is already balanced. Fourth, balance the hydrogen atoms. There are 4 hydrogen atoms in methane and 2 in water. To balance hydrogen, we change the coefficient of water to 2 methane plus oxygen yields carbon dioxide and 2 water molecules. Fifth, balance the oxygen atoms. Now we have 2 oxygen atoms in carbon dioxide and 4 in water, totaling 6 oxygen atoms on the product side. We need 3 oxygen molecules to provide 6 oxygen atoms. Methane plus 3 oxygen molecules yields carbon dioxide and 2 water molecules. Finally, verify the balance. We have 1 carbon, 4 hydrogens, and 6 oxygens on both sides. The equation is balanced. This example shows how to systematically approach balancing chemical equations. Mastering this skill is essential for accurate chemical analysis and problem solving. Mass stoichiometry is a branch of chemistry that deals with the calculation of the masses of reactants and products in a chemical reaction. It uses balanced chemical equations to relate the masses of different substances involved. In essence, stoichiometry allows us to predict how much of each substance we need or will produce. This is particularly useful in laboratory settings, industrial processes, and even in everyday applications like cooking. The foundation of mass stoichiometry is the mole concept. A mole represents 6.022 times 10 to the power of 23 particles of a substance. This number, known as Avogadro's number, allows chemists to count atoms and molecules by weighing them. Using the balanced chemical equation, we can determine the mole ratio between reactants and products. This ratio helps us convert between the mass of one substance and the mass of another. Understanding mass stoichiometry is crucial for anyone studying chemistry. It bridges the gap between theoretical equations and practical laboratory work, enabling precise control over chemical reactions. Relevance of mass stoichiometry. Mass stoichiometry is not just an academic exercise. It has significant practical applications. In industries, it ensures that chemical processes are efficient and cost-effective. For example, in pharmaceutical manufacturing, precise stoichiometric calculations ensure the correct dosage of active ingredients. In environmental science, stoichiometry helps in understanding pollutant formation and degradation. By knowing the exact amounts of reactants, scientists can design processes to minimize harmful emissions. In everyday life, Cooking is a simple analogy. Recipes are like chemical equations. If you know the right proportions of ingredients or reactants, you can predict the amount of food or product you'll make. This concept helps in scaling recipes up or down. Moreover, stoichiometry is essential in research and development. Scientists use it to design experiments and develop new materials. Accurate stoichiometric calculations ensure that experiments are reproducible and results are reliable. In summary, mass stoichiometry is vital for various fields. It ensures the accuracy and efficiency of chemical processes, from industrial production to environmental management and scientific research. Calculating mass of reactants or products. Step-by-step guide. Calculating the mass of reactants or products using a balanced chemical equation involves several steps. Here's a straightforward guide to follow. First, write the balanced chemical equation for the reaction. This equation provides the mole ratio of reactants and products. Second, convert the given mass of a substance to moles using its molar mass. The molar mass is the mass of 1 mole of the substance, usually given in grams per mole or g-mole. Third, use the mole ratio from the balanced equation to convert the moles of the given substance to moles of the desired substance. This step involves simple multiplication based on the coefficients in the equation. Fourth, convert the moles of the desired substance back to mass, using its molar mass. This gives you the mass of the reactant or product. These steps ensure that you can accurately determine the amount of reactants needed or products formed. Let's apply this method in a practical example in the next section. Example: calculation, mass of reactants. Consider the reaction of nitrogen and hydrogen to form ammonia. Nitrogen gas plus 3 molecules of hydrogen gas yield 2 molecules of ammonia. Suppose we need to find the mass of hydrogen required to react with 28 grams of nitrogen. First, write the balanced equation. Nitrogen gas plus 3 molecules of hydrogen gas yield 2 molecules of ammonia. Second, convert the mass of nitrogen to moles. The molar mass of nitrogen, N2, is 28 grams per mole. Thus, 28 grams of nitrogen is 1 mole. 28 grams divided by 28 grams per mole equals 1 mole. Third, use the mole ratio from the equation to find moles of hydrogen needed. The ratio is 1 mole of nitrogen to 3 moles of hydrogen. 1 mole of nitrogen times 3 moles of hydrogen per 1 mole of nitrogen equals 3 moles of hydrogen. Fourth, convert the moles of hydrogen to mass. The molar mass of hydrogen, H2, is 2 grams per mole. Thus, 3 moles of hydrogen is 3 moles times 2 grams per mole equals 6 grams. Therefore, 6 grams of hydrogen are required to react with 28 grams of nitrogen. This example illustrates how stoichiometry helps in determining the precise amounts of reactants needed. Example: calculation, mass of products. Now, let's calculate the mass of ammonia produced from the same reaction. Nitrogen plus hydrogen yields ammonia. Suppose we start with 28 grams of nitrogen and 6 grams of hydrogen. First, verify the balanced equation. Nitrogen plus hydrogen yields ammonia. Second, convert the mass of nitrogen to moles. 28 grams divided by 28 grams per mole equals 1 mole. Third, convert the mass of hydrogen to moles. 6 grams divided by 2 grams per mole equals 3 moles. Fourth, use the mole ratio to find moles of ammonia produced. The ratio is 1 mole of nitrogen to 2 moles of ammonia. 1 mole of nitrogen times 2 moles of ammonia over 1 mole of nitrogen equals 2 moles of ammonia. Fifth, convert the moles of ammonia to mass. The molar mass of ammonia is 17 grams per mole. Thus, 2 moles of ammonia is 2 moles times 17 grams per mole equals 34 grams. Therefore, 34 grams of ammonia are produced from 28 grams of nitrogen and 6 grams of hydrogen. This calculation demonstrates how stoichiometry helps in predicting the amount of products formed. Understanding limiting reagents. In many chemical reactions, one reactant is consumed before the others, stopping the reaction. This reactant is called the limiting reagent. It determines the maximum amount of product that can be formed. To identify the limiting reagent, compare the mole ratio of the reactants used to the ratio in the balanced equation. The reactant that produces the least amount of product is the limiting reagent. For example, consider the reaction A plus B yields C. If you have 1 mole of A and 1 mole of B, B is the limiting reagent because you need 2 moles of B for each mole of A. Limiting reagents are crucial in chemical manufacturing. Knowing the limiting reagent helps optimize the use of resources and reduce waste. It ensures that reactions are efficient and cost-effective. Understanding limiting reagents also helps in laboratory experiments. It ensures that experiments are designed correctly and that the expected amounts of products are obtained. Practical example involving limiting reagents. Let's revisit our ammonia production example to identify the limiting reagent. Suppose we have 28 grams of nitrogen and 10 grams of hydrogen. Convert the masses to moles. For nitrogen, 28 grams equals 1 mole. For hydrogen, 10 grams equals 5 moles. Use the mole ratio to determine the limiting reagent. 1 mole of nitrogen requires 3 moles of hydrogen. Nitrogen is the limiting reagent. Identifying the limiting reagent helps predict the correct amount of product. Conclusion: the importance of balancing equations and stoichiometry. Balancing chemical equations and understanding stoichiometry are fundamental skills in chemistry. They ensure the conservation of mass and charge, providing accurate representations of chemical reactions. Through systematic steps, balancing equations becomes manageable. This skill is essential for predicting reactant and product amounts, optimizing chemical processes, and conducting precise laboratory experiments. Mass stoichiometry connects theoretical equations to practical applications. It is crucial in industries, environmental science, and everyday life. Identifying limiting reagents further enhances the efficiency and accuracy of chemical reactions. In summary, mastering these concepts opens the door to a deeper understanding of chemistry. It enables accurate predictions, efficient processes, and innovative solutions. Balancing equations and stoichiometry are the cornerstones of chemical analysis and problem solving. Remember, chemistry is not just about memorizing formulas and equations, it's about understanding the world around us and solving real-world problems. Keep practicing, stay curious, and never hesitate to explore further. The world of chemistry is vast and full of wonders waiting to be discovered. If you enjoyed this video, please like, share, and subscribe for more insightful content. Make sure to have a nice night and good night.